the computational basis of the clustering problem. Clustering patients. Welcome back to the clustering problem. After we understood why we want to cluster our patients, let's see how we make it happen. The goal of deriving archetypes out from the data, or in other words, clustering patients, also known as data points, into groups of similar properties is a well-known goal in the space of unsupervised machine learning. Going back to our EMR example, we need an algorithm that will define these patients as belonging to cluster number 1, these patients to cluster number 2, and these to number 3. In other words, we need an algorithm that will define the archetypes. What are the regions? What are the definitions, if you will, of each cluster? These are actually the circles you see here. In mathematical terms, the correct clustering could be defined, for example, as partitioning that will cause the intra-cluster distances to be minimal and the inter-cluster distances to be maximal. How can computers discover such clusters? Are they able to find the best partitioning? Well, they can't. Wait, what did you say? Computers can't discover the right clusters for sure. They can't calculate what is the best partitioning of data points into clusters. They don't have enough time for that. They don't have time for that? Excuse me? What the? Yes, partitioning data points into groups may sound simple, but it's not. If indeed we want to find the best partitioning, the best clustering, we need to calculate and assign a score to each clustering option, then output the option with the best score. Calculating the score is not trivial. There are many ways even to define what is a good score. Nevertheless, from a complexity point of view, it's quite an easy computation. We can think of a simple mathematical formula like this one. The smaller the intra-cluster distances are, and the larger the inter-cluster distances are, so will the score be lower, which means, in this case, better. However, calculating such score for each clustering option is hard. Actually, extremely hard. This is because there are millions and billions and potentially gazillions of clustering options, even if the dataset is not very big. Experimentation time. How many options are there to cluster just 100 patients into just 2 groups? Maybe 100 squared? Maybe factorial of 100? Well, let's say the first patient goes here. Now he is a group of 1 patient. The second patient has 2 options, either to join the group of the first patient or to go to the second group. The third patient has also 2 options, either to join the group of the first patient or go to the second group. So, for each of the 2 options of the second patient, we have 2 options for the third patient. Altogether, 4 clustering options. Similarly, the fourth patient has also 2 options, and that will lead us to 8 different clustering options. The formula here is that the number of clustering options equals to 2 to the power of 100 minus 1. This is the first patient. The order of magnitude is 2 to the power of number of patients, or let's say the number of clusters to the power of the number of patients. This series will continue to grow exponentially as we add more and more patients. By the time we get to the 100th patient, even for just 2 clusters, this is the number of clustering options that we get. This exponential complexity can lead us to a point where the calculation is not realistic or not even possible. Even with relatively small datasets, we will see that the number of required calculations is so big that it is even larger than the number of molecules in the atmosphere, which is estimated to be this number. When I say that the calculation is not possible, I mean that even if calculating the score of one clustering option takes 1 millisecond, there could be so many clustering options that it's possible to show that even if we take all the computers in the world and make them work together on this problem alone, it will still take them years to go over all the clustering options. In computational complexity theory, we define such problems under a certain class. These are the problems where the time required to solve them increases exponentially as the size of the problem grows linearly. When we encounter a problem that belongs to this class of problems, it means that we need an algorithm that uses some heuristics. Such algorithm does not examine all the possible solutions to the problem, but applies some educated guesses in order to find a good solution to the problem in a reasonable time. In the next unit, we will see such an algorithm that solves the clustering problem in a very short time. Wait, but I've just finally understood why computers can't discover the right clusters. They can discover the right clusters for sure. You see, when we use heuristics, when we use educated guesses, even if they are very good, we cannot be 100% certain that we end up with the optimal solution to the problem every single time. More on that in the following units. For now, I just hope you understand that some problems cannot be really solved or computed in a reasonable time. If you work with a certain statistical or machine learning software and you see a nice button that says clustering, be suspicious with its result. No one can guarantee that it produces the correct clustering. So, let's start making it a reality. Let's start guessing how to find a good solution.